Hello, welcome to this video. In this, let us discuss about resonance. Do you know the marching of soldiers are not allowed on the bridge? It is because their marching can set vibration at the bridge's natural frequency. The bridge can break apart if the footsteps resonate with the natural frequency of the bridge, which may lead to its destruction. The Tacoma Bridge tragedy happened in the year 1940. The bridge collapsed at wind speed as low as 56 km per hour. The underlying physics can be explained by the phenomenon of resonance. Now let us check how we can define resonance. Resonance may be defined as the phenomenon of making a body vibrate with its natural frequency under the influence of another vibrating body with the same frequency. Now, let us derive the condition for resonance. Resonance occurs when applied frequency is equal to the natural frequency of the system. At resonance, the system oscillates with maximum amplitude. We know the expression for amplitude in the case of forced oscillation, and it is given as A is equal to F naught divided by square root of omega square minus p square whole square minus 4b square into p square, where omega is the natural frequency of a system and p is the frequency of driving force. So we know at resonance amplitude is maximum. So amplitude becomes maximum when denominator is minimum. So to get that condition, we need to differentiate denominator with respect to p. So when it becomes or when it is equal to 0, we will get maximum amplitude. So now if we differentiate denominator with respect to p, we will get 2 into omega square minus p square into minus 2p plus 4b square into 2p, which is equal to 0. So 2 into minus 2, so minus 4p into omega square minus p square plus 4b square into 8b square p. So we can take 4p out, so that we will get 4p into minus omega square minus p square plus 2b square, which is equal to 0. So in this, p is the frequency of driving force, which never be 0. So only solution is the term which are there inside the bracket must be equal to 0. So then we can write omega square minus p square, which is equal to 2b square. So we can write p square equal to omega square minus 2b square. So from this expression we can write the expression for p as square root of omega square minus 2b square. So when the frequency of driving force is equal to square root of omega square minus 2b square, the amplitude become maximum, or we will get the resonance condition. Now let us derive an expression for sharpness of resonance. We know in forced oscillation, the amplitude of oscillation is given by the expression F naught divided by square root of omega square minus p square whole square plus 4b square p square. Here the value of p is given as the square root of omega square minus 2b square. So when we substitute the value of this, we will get the expression for A max, because at resonance the amplitude of oscillation is maximum. So when we substitute this, we will get the expression for A max as f naught divided by square root of omega square minus 2b square whole square plus 4b square into omega square minus 2b square. So simplify this so that we will get A max equal to f naught divided by square root of 4b power 4 plus 4b square omega square minus 8b power 4. So if we add 4b power 4 to minus 8b power 4, we will get minus 4b power 4. So the remaining expression become A max equal to f naught divided by square root of 4b square omega square minus 4b power 4. So let me take 4b square as common in this, so that I will get A max equal to f naught divided by square root of 4b square into omega square minus b square. So if we take 4b square outside the square root, then we will get A max equal to f naught divided by 2b into square root of omega square minus b square. So let me substitute like this. So let us make small rearrangement. We can write like this: A max equal to f naught divided by 2b into square root of omega square minus 2b square plus b square. So when you add this, it will become minus b square. But we know omega square minus 2b square is nothing but p. So substitute the value of p. So we will get the expression as A max equal to f naught divided by 2b into square root of p square plus b square. Here p represents the frequency of driving force and b represent the damping frequency. So if the damping is very low, that means B is low, then we can write the expression as A max equal to F divided by 2 into BP. So one thing we need to make sure, say at resonance, the amplitude of oscillation is maximum. The amplitude of oscillation is a function of the damping frequency as well as the frequency of the driving force. Now if we plot a graph of amplitude versus frequency, we can observe how the amplitude at resonance varies at different damping mediums. If the damping is heavy, then at resonance amplitude may be smaller. If the damping coefficient keep on decreasing, then at resonance the amplitude keep on increasing, and if damping coefficient is 0, the amplitude at resonance may be infinite. So we may come to the conclusion, if smaller the damping, then sharper the resonance. Thank you for watching this video.